Hey guys! So the question that we're going to solve today is in-order traversal of a binary tree using a stack. This question can also be solved in a recursive way, but I'll make a video on that one later on, but today we're going to do it using stack. One thing I would just like to say is that this question is marked as easy on Leetcode, but if you're just beginning, don't be intimidated, don't feel bad that you needed help. We have to begin somewhere, and to be honest, using a stack, this question is not that intuitive. Um, okay, with that said, let's just get started. Okay, so this is the question on Leetcode. Binary tree in-order traversal. They've already given us an example, but we're going to look at a different one. So this is the example. You would be given the root node, which in our case is actually 1. So this is what you're given, and this is the tree. For those who don't know how in-order traversal is done, we're going to write down the in-order traversal for this one. Let's use a different color for this. So what is the in-order traversal going to look like? In in-order traversal, you go to the left of the node first, then you visit the node itself, and then you go to its right. So for example, when you start off with 1, you want to go to its left, which is 2. Then you would want to continue going to its left, but there's nothing here, there's null. So then you would visit the node itself. Then you would go to its right, which is 3. Do we write down 3 here? No, because we want to visit the left first. So we would go to 4. 4 has no left, no right, so we're going to come back from it, and then we end up visiting it. And then we go back to 3, so we're going to visit 3, because before visiting the right, we have to visit the node itself. And then there's 5. You go back. So now when we come back here, we're done traversing the left. So we want to visit the node 1, and then we want to continue going to the right side. After going to the right, we want to go to the left, but there's nothing there. We come back, we visit it, we go to the right, there's nothing there, we come back. So this is what the in-order traversal is going to look like, right? So now where does the stack come into picture? If you notice, when we are visiting the left, we want to come back to the node itself because we want to go to its right too. So we want to store the node somewhere, every node that we're visiting. After I came back to, let's say, 3, and I went to 4, there could have been more nodes here, but I want to come back to 3 in order to be able to go to 5. So that's why we need a stack to store the nodes that we're visiting, so that in the end we can visit their right too. So to start off, what we're going to do is, and also because we want to traverse, we want to keep traversing, we want sort of like a pointer that is taking us through the tree, but we don't want to use the root itself, because the root was given to you, it was pointing to 1, represents a perfectly good tree, so you don't want to change the root to point to something else. So we're going to use a pointer called current, and we're going to start off by setting it to where the root is, so it would be pointing to 1. Now we want to add 1 to the stack, right? So we added 1 to the stack, and now we want to go to the left. So we want to move the current to point to the left of wherever it is pointing right now, which is 2. So moved it, and then we want to move, according to the logic, we're going to continue moving to its left. But before moving to its left, wherever the current is pointing, I'm going to store that value to the stack, and then I'm going to point the current to the left of wherever it is right now. The current is here right now. I want to make the current point to the left. So it will be moved here. Now, we notice 2 things, that we're adding wherever we are, the current node to the stack, and then we're moving the current from wherever it is pointing right now to its left node. So when we come to null, do we want to add null to the stack? No, right? There's no point. So we want to stop adding nodes to the stack when we reach a null. So what we have learned so far is that we want to keep looping while current is not equal to null, right? We want to stop there the moment it starts pointing to null. And what were we doing? We were pushing the value to the stack.push. I am writing this in Java, so whatever current is pointing to, right? This was the first step that we were doing, and then we were moving the current to its left. Current dot left. So these are the things that we've established so far, and we're not adding the null. So what would happen is that it would come out of this loop. Now that it has come out of the loop, and but the current is still pointing to null, what do I want to do? I'm done traversing the left side. So if you notice, if you look at the traversal, when you're done traversing the left side of the node, you want to visit the node itself. So visiting could mean that either you peek the value or you pop. Peeking would mean essentially that you just look at the value that is on the top, but you don't remove it from the stack. But do I need to keep 2 in the stack? No, right? Because even if 2 is removed, I can still use it because I can just take that value in something. And I can just go to its right. So when I take out 2, I would have this node. It is still pointing, its right is still pointing to 3. So I have access to the right side. And to go back to the top, I already have 1 on the stack. So I want to pop this. I want to pop it. So the first step is stack.pop, because I want to remove that value. But I also want to have that value somewhere. I can just print it out because I want to visit it. But I want to move the current that is on null to somewhere else, right? Null is not going to take me anywhere. So I want to move the null from here to here. So what that means is that I am basically changing my current to point to this. So now current is equal to stack.pop. So basically it's pointing at 2 right now. 2 is removed from the stack when I'm done popping. And now I can just, let's say we're storing this in something called results, right? So I can just add this current's value to my results. Results.add, and you want to add current or its value. So now we're done. So we popped 2, we have it in the results as well. Now I want to move to the right of this. So what I basically want to do is I want to move my current to point to current dot right, because I want to go back to the right side of this. So what would this do? This would move it from here to here. And now we're at a different node. We can continue with this logic. We can just go back to this logic again. So what is the condition for this one going to be? We know that this has to be a while loop, but what are the conditions going to be? So one is, I want to keep traversing if there's more nodes here, right? Because when I'm on 3, it's going to add more values. So I want to keep traversing till the stack is not empty. Is empty. So I want to keep traversing till the stack is not empty. But also, when you start off, was there anything here in the stack? No, right? There were no values over here. It was empty. But you wanted it to go inside this. So you're going to check that something is not null. Now that something could be your root, or could be the current. Now, if you, for the first time for it to get in, checking that the root is not null is perfectly fine, right? If in case the root itself is null, it wasn't pointing to anything, you don't want to traverse or you don't want to do anything. So you can add root here, but adding root would not, what would happen? This loop will not exit because the root's value is never going to be null. So you cannot have that over here. So what we want to have is current is not equal to null. Because remember, before we even hit this, we made our current point to wherever the root was. That is one thing. And the other reason why you want to keep this as not equal to null is that you are going to end up in a situation where you're going to hit the leaf nodes too, right? In which case both left and right are going to be null. And towards the end of it, let's say you're at this, the stack is going to be empty. You've traversed everything. Um, but in the end, when your current is also pointing to the null and your stack is empty, you want to exit out. You don't want to do anything. So that's why current is not equal to null is our condition. So this is the code. This is basically it. I use the Java structure, so this is perfectly fine, but we're going to code it out and check if the example that we've been looking at works or not. So let's do it. So as we talked, we're going to need results, right? We're going to store it in a list. This is in Java. So we're going to create a list of integer to store the results. Let's use an array list. Okay. Another thing that we need is a stack of tree node, not integers, tree node, because we want to store the node itself, because we want to be able to go to its right. Let's just call it stack is equal to new stack. Great. Now this is where our while condition hits, right? So while the stack is not empty, stack dot is empty not. So while the stack is not empty, oh yeah, I want to have a tree node called current, and I want to make it point to the root first, wherever the root is pointing, right? Okay, so while the stack is not empty and while current is not equal to null, these are the two conditions we want to use. So till this point, I want to keep traversing. And in the end, I want to return the results. Now, in this while, we had a while again. While my current is not pointing to null. This was the condition we used, if you remember, if you look at the tree for this node, right? I explained using this node that we don't want to add it to the stack, so we want to come out of there. So the current should not be pointing to null for us to be able to do that. So first thing we did was we pushed the current to the stack. Second thing we did was we moved the current to the left. We made it point to the left. So current is equal to current dot left, right? After coming out from here, what did we do? When we were done traversing the left, we came back to the to 2. We wanted to make it point to the right. That was one thing that we wanted to do, but we also wanted to pop it and add the value to the result. So that's exactly what we're going to do. So stack dot pop, but I wanted to have that value in something. So what I did was I made my current point to the popped value, added this, then I added it to the results. So results dot add, and I added current dot val. You don't want to add the node, you want to add the val, because the results is expected to be it needs to have integers in it. So this was the one thing that we did, which is basically like visiting it. And then you want to move your current to the current's right? So when we came back from here, we were pointing to 2 and we wanted to move to 3. So current is equal to current dot right. And that is it. That is the code. Let's try running this. It is accepted. Let's use our case. 1 2 0 1 2 0 null 3 null null 4 and 5. That is our case. So we ran it. Oh yeah, it actually ran that already. The output is 2 4 3 5 1 0 2 4 3 5 1 0. So this works perfectly fine. Let's try to submit it. Okay, great. It's been accepted. And now let's talk the last thing, time complexity and space complexity. So for time complexity, we ended up visiting all the nodes, right? So because you have to traverse throughout the tree once at least to just add them to the result set. So the time complexity is going to be O of n. What is the space complexity going to be? So in the worst case, we can have a skewed tree, right? Something like 1, 2, 4, 5, 6. So you'll end up adding all the nodes to your stack because you're just visiting. So that means whatever the height is of this tree, that is what the worst space complexity of the tree would be. So the time complexity is going to be O of n, and space complexity is going to be O of h, the height of the tree. That is it. I hope this video helped you guys. Bye and have a good day.